Good morning, good afternoon, and good evening, everyone. The authors and invited guests, welcome to Technical Session 10A. I'm Sanskriti Khamkar, and I will be moderating this session. On behalf of the Global Knowledge Research Foundation and GR Scholastic, it is my pleasure to welcome you to the 11th International Congress on Information and Communication Technology. That is ICICT 2026 in London, UK. This edition of the conference is being conducted in a hybrid mode. The physical event was held on the 24th in London, and the virtual sessions are being conducted via Zoom from 25th to 27th February 2026. I hope you find today's session engaging, informative, and insightful. In this session, we have 6 presentations. Each presenter will have 12 minutes for their presentation, followed by 3 minutes for question and answers. I will give a gentle reminder when 2 minutes remain. I request all participants to stay connected until the closing remarks. If you have any questions or updates, feel free to share them in the chat box. I'd also like to apologize in advance for any mispronunciation of names during the session. Now, before we begin, I'd like to introduce our session chairs. First, we have Dr. Fehmi Zafar. Dr. Fehmi is an associate professor at the University de Quebec et Cotonou, UQAC, specializing in cybersecurity, IoT security, and machine learning applications. His research focuses on cybersecurity and artificial intelligence, particularly IoT security, blockchain technologies, and the use of machine learning for threat detection, contributing to the development of secure and intelligent digital systems. Our co-session chair is Dr. Deepika Birari, who is an assistant professor in Information Technology Department at Army Institute of Technology, Pune. She has total 8 years of teaching experience. Dr. Deepika has published more than 20 research papers in various Scopus indexed and UGC-approved journals and conferences. She has 4 patents publications and 1 patent grant. Currently, she's associated with research work in different domains like image processing, machine learning, data mining, and artificial intelligence. Would you please like to share a few words with us, ma'am?
Hello, am I audible?
Yes, ma'am, you're audible.
Yeah. Thank you so much, ma'am, for the kind introduction. And now we can start with the presentation.
Yes. Our first presenter is Joseph Eckert, who is presenting paper titled A Cost-Efficient Digital Approach to Determining Engine Rotation.
My name is Joseph Eckroat. I am a student at the University of North Dakota in their electrical engineering department. I'm here to present my cost-efficient digital approach to determining engine rotation. So the hows and whys of rotational speed. So rotation is usually measured directly through tachometers, physical, magnetic, optical, or even more specialized varieties. And specifically, we were interested in the rotation of internal combustion engines. And these engines typically produce strong vibrations due to the weight of the internal components and the actual combustion. And the position and rotation of the crankshaft is critical for engine timing to help prevent misfires, or just due to like air fuel ratio mixes and or premature detonation. And combustion engines typically use a magnetic or an inductive crankshaft sensor that is hard to reach and service because it's typically deep down in the in the engine bay covered by hoses, all kinds of manner of different internal components, basically. And so what we propose to do is find an easy to apply and non-destructive method of determining the rotation of the internal combustion engine, making use of cheap, easy to acquire parts, and then doing so use signal analysis to determine the rotations per minute of that engine. So to begin, the prototype used a ceramic piezoelectric vibration sensor. These are found, they're very common, typically found in like children's or kids' kits for like beginning vibration. This one in particular is the EK 1952 was, I'm pretty sure, acquired off of Amazon for probably like $1. Um, and we used a MIDAC to help gather data. And then we used the digital and for transfer suite in Simulink, which is a MATLAB product. And then we tied that to a K24 A1 engine, which is mounted in a 2006 Honda CRV. I'm pretty sure Honda produced millions of these engines. They're just about everywhere, and it's a very good example of what a typical engine is going to look like. So to begin, we needed to figure out if this sensor that was very cheap is even capable of doing what we're requesting it to do. So first we looked at just what its steady state, output would look like. So it looked like it usually made noise around 60 hertz with a very low amplitude of about 1.5 millivolts, just sinusoidal, purely sinusoidal. And then we gave it sharp impulse responses to determine how it would act. That's got a very high gain on it, and which kind of led into lower oscillations than about the 50 to 60 hertz range. They weren't completely consistent, which is a bit odd, but for what we're looking for, it's way outside of the scope that we're looking for. It's going to be, those small oscillations are going to be completely covered by the amount of noise that goes on in an internal combustion engine. So next, we need to verify the concept that it would be able to determine and accurately figure out the frequency of a perfectly sinusoidal input. So we used an FS90R servo. It's those little like servos you get, a constant velocity servo you get in like a lot of kits. It's acts at about 110 RPMs at about 5 volts. It resulted in peak-to-peak voltage of a little less than a volt and a frequency of about 7.625 hertz, which when you do the math comes out to be about 114 RPM. So that shows that we can use this very cheap piezoelectric sensor to determine sinusoidal vibrations. And this was all done on like a tabletop made of like wood. So it wasn't anything particularly fancy or laboratory specific. So it could work in a typical day-to-day scenario. So then we scaled up the concept to the actual engine itself, which you can see that cheap piezoelectric sensor is held on with Scotch tape on the top of the engine, excuse me. And first, it was just ran, data was gathered, and then we used that to fine tune the model first. And then later on, we ran it in real time off of just a locally held laptop. So nothing too special there. So we can see the actual data gained here, or excuse me, acquired. It's very noisy. It looks awful, which not a surprise considering it's attached to an entire vehicle with everything else going on. There's water pumps, coolant pumps. You have, HVAC fans and everything else going on there. So it had a considerable amount of noise. So then their next step was to analyze this noise and figure out if from this data we can dig out what the actual vibrations coming from like the crankshaft or combustion. So we did a spectrum analysis, used a Blackman window with a length of about 8200. We wanted a good, we had a very narrow band of harmonics we were looking for. So we can kind of picture in exactly what narrow in exactly what we were looking for in here. And we can see the spike at around 23 hertz right up here. So this is kind of what we're looking for. And down here, once you get past about 200 hertz, we can see it gets very noisy very fast. And so we're not really interested in this. So then our next step well, actually, first, this is a lot of text, but I'll briefly summarize this all up really fast. So engine vibration greatly depends on the configuration of the engine, whether it be an inline engine, a V style engine, or even like a flat four, for instance. An inline four engine, which is used here in this example, is one of probably the most common types of engine outside of an inline three. They don't have much vibration in the X or Y axis due to the way it's oriented. They're semi-stable. The primary or the first order vibration we're seeing on that spectrum analysis is tied to the speed of the crankshaft. That's what we consider the first order, which is primarily caused by the movement of the cylinders and the weight of the crankshaft spinning, which is oftentimes why you see cars with harmonic balancers. But half of the primary is the actual firing of the cylinders, and that's actually what has the strongest vibration. And it's equal to about half of the number of cylinders is about where you would see that frequency at. So, for example, a V8 would have the highest order vibration at about 4 times the crankshaft frequency in a four-stroke engine because it goes up and down 4 times before it actually combusts, or has 4 strokes before it goes. And so because it's an inline four in this 2006 CRV, we can expect the highest order vibrational frequency to be at about twice the crankshaft rotations because it has 4 divided by 2 is 2. So our frequency band of interest is about 20 hertz to 200 hertz, which correlates, as mentioned, because we're converting from frequency to RPM and accounting for the number of cylinders that we can expect is that 20 hertz, 200 hertz correlates to about 600 to 6,000 crankshaft RPM, which is the typical working range of a vehicle. We're not looking past 6,000 RPM for a Honda CRV, but past that point, it's going to be redlining up to like the moon. So we got bigger problems if it's past that. And under 600, it was kind of what we're looking for, stuff that falls out of the normal and means that there is a problem. So we're testing between 750 to 4,000 crankshaft RPM. So as a summary, we had a low and high pass filter. This is just a basic. The pass band of 175, 200. If we get past it, if you loosen it up too much, a lot of noise starts to come through. And on the high pass filter down low, there's some really strong signals and in the low frequency range from just very strong slow ones from just the fact that it's just a car, and so there's a lot of thumping and even when it's not moving. So you have to really clean those out. So it needs a very strong attenuation at the low frequency, and then we apply the gain of 50, which is optional. That's just to bring the values up closer to 1. So and then here we can see the filtered and unfiltered, and unfiltered in blue, filtered in orange, and you can see here in the gaps here in the middle where you can see where the radiator fan kicked on and the engine has worked a little harder for the radiator fan. So it was interesting to see that come through after we applied some of this initial filtering. So keep this short too. Use fast Fourier transforms. We use a sampling rate of about 5,000 hertz, which allows the harmonics up to 2,500, way beyond our range of interest. But we found that if we do not do so, a lot of that noise ends up showing up in the lower bands. So we have to capture them in order to remove them. We use a sample size of about 4,100, obviously the nearest power of 2 equivalent. And we're trying to strike a balance between update speed and resolution. So with an FFT resolution, we got about 36 RPMs, updating about every 0.82 seconds. It was trying to be a balance between the two. So we can see here a tested idle, unfiltered in blue, after bandpass filtering in green, and then some small additional filtering and so on and so forth, and analysis gets our RPM here. And we can see it very closely matches to what the actual tachometer on the vehicle is showing. And you can even see where it spiked slightly when the radiator fan kicked on, because it was a hot day when we did this testing. And you could see it kicks on, then it kicks off, and kicks on, and kicks off. Next, we tested an impulse response, quick, sharp accelerator pedal depressions. You can see them, they were captured here pretty consistently. We try to be consistent as possible when we apply the accelerator. You can see it spiked and then dropped and then went back to idle and then spiked and then dropped and then went back to idle. I mean, this is a 20-year-old car, so it's it lags a little bit when it catches back up to idle again. So our idle showed a very strong correlation between the vehicle's tachometer and the results found using the cheap piezoelectric sensor data. Sharp applications of the accelerator pedal, while harder to definitively determine how accurate it was relatively close to what we were getting to when we were manually depressing the pedal, trying to simulate an impulse response. We went a little further. While not included in this, we did do some further testing. We found that you can actually apply the sensor to the outside of the vehicle without even lifting the hood and still get pretty good data or accurate data. It didn't have much of a degradation on accuracy, which is interesting and a point of further research if you not even have to even lift the hood. So it shows the concept of the system works to provide a pretty cost-effective and non-invasive method of determining an RPM, not with relative accuracy. So, any questions?
Thank you. Thank you very much for your good presentation. It was clear. I would like just to ask whether there is a comparison with the state of the art, whether did you see if there are other papers, other work done in the same context by other researchers?
We hadn't seen anything directly. No one had really had interest in just grabbing a dollar sensor off of Amazon and slapping it onto the side of a vehicle and seeing what happens. State of the art, absolutely. There's all kinds of stuff out there about people who attach, incredibly advanced sensors to these crankshafts to determine what they're doing with minute details. But that involves, you have to remove part of the engine bay to get in there and apply all this stuff. And we were looking just to try something you slap on the side of a vehicle. And you can just determine if the engine, and you can catch misfires in the act without even having to even lift the hood in some cases. So, but yeah, so.
Yeah. Okay. Thank you. Thank you so much. Great work.
Yeah. Thank you.
If no more question, I think we can move to the second paper.
Yes. Dr. Gupta, would you like to ask any questions?
No questions from my side. We can move on
Thank you.
for the next presentation.
Thank you, Mr. Joseph, for your presentation. And Dr. Bell, any questions? Next, we have Munira Al-Saidi presenting a quality-invariant deep learning framework for degraded crime scene fingerprint forensic matching under adverse conditions.
Hello, can you hear me, please?
Yes, we are the
Okay. Okay, good evening, everyone. My name is Dr. Munira Abd Hamdi Al-Saidi. I'm a lecturer in the Intelligent Medical System Department in the Biomedical Informatics College at the University of Information Technology and Communication in Baghdad, Iraq. So it is my honor to present the work titled A Quality Invariance Deep Learning Framework for Degrade Crime Sense Fingerprint Forensic Matching Under Adverse Condition. So, as we know all, in real crime sense, fingerprints are rarely captured under idle laboratory conditions. They are usually degraded due to dirt, moisture, smudge, partial impression, and physical distortion. So this uncontrolled environment actually affects and reduce the reliability of traditional fingerprint matching systems. So in this research, we address this critical challenge by proposing a deep learning framework that learns structural correlations directly from the graded fingerprint image. So before explain the crime identification, I will pass through the traditional or the normal definition of identification. Identification is the process of validating or figuring out the identity of a person. So it answers the question, who is this? Whereas crime identification is the process of validating the identity of someone or something, such as object, biological trace, by comparing unknown evidence to new or known data. So typically, accurate identification is critical in forensic investigation because it directly affect justice, legal decisions, and criminal responsibilities. So in criminal investigations, the main traditional way to identify the identity of a person, usually they use biometric traces, and there are two kind of biometrics, physiological biometrics and behavioral. Physiological biometric such as fingerprint, face recognition, iris recognition, and these are physical characteristics of a human body that are unique and relatively permanent. So as an example, fingerprint based on unique ridge patterns that don't change through life. For the behavior biometric, such as walking pattern, key stroke pattern, voice or talking pattern. These are based on how a person behave rather than their physical structure. So as an example, walking pattern, usually every individual has a distinctive walking style. So for problem definition, we have two important questions. The first one, why biometric? There are five essential criteria that make a biometric trait suitable for identification. The first one, universality. It means everyone should have the trait. Uniqueness. It means the trait must be different for every individual. Permanence. The trait should remain stable over time. Collectability means the trait must measurable and easy to capture. And finally, acceptability. It means people must be willing to use it. The second important question, why fingerprint? So according to a criminal investigator, fingerprint are one of the most reliable biometric identifiers because they allow they follow three fundamental scientific principles. The first one, fingerprints individual characteristic. It means every fingerprint is unique. No two people have identical fingerprint, not even for identical twins. The first point, fingerprint permanence. Fingerprint ridge patterns remain unchanged from birth to death. However, the print itself may change due to permanent scars and skin disease. And the last point, fingerprint general ridge patterns. This allow for systematic classification. So here in this pie chart, here in this pie chart, we shows the distribution of biometric technologies usage in identification systems. So here, as shown, we can see the largest portion is for finger scan at 48.8% compared to other biometric scans such as facial scan, iris scan, keystroke scan. The other chart represent the rapid growth and the importance of advancement in fingerprint identification technology during the period of 1999 to 2005. So in biometric identification system, there are two different authentication method, verification and identification. Verification performs one-to-one matching, so it checks whether a person is truly who they claim to be, and it relies on both identity information and biometric data, whereas identification performs one-to-many matching, so it determines who a person by comparing their biometric sample with all records in the dataset. The main challenge in fingerprint identification system is the low quality fingerprint image. So noise, rotation, blur, distortion, and partial prints make it difficult to accurately extract minutiae such as ridge, ending, and bifurcation. Therefore, traditional localized feature-based methods are often insufficient, requiring more robust enhancement or deep learning-based approach for reliable matching. Most automated fingerprint identification system rely on minutiae matching during the comparison stage. So the core idea here is to extract distinctive local features from the fingerprint image called minutiae point, such as ridge termination and ridge bifurcation. Then the system compares the numbers, the position, the orientation of these minutiae point with stored template to determine a match. Usually each feature has three parameters, X, Y, and theta. X represent the horizontal position of the minutiae point in the fingerprint. Y represent the vertical position of the minutiae point in the fingerprint image, while theta represent the local ridge direction at the minutiae points. For related work, most traditional approaches of fingerprint recognition system involves feature-based approach, template-based approach, or even deep learning approach. For first approach, they enhance ridge texture and orientation, then extracts discriminative features for matching. This approach is effective for degrade fingerprint image. The second method, the template-based approach, it extracts and stores key minutiae as compact template and then matches these templates with the stored or with instead of the raw image. Also, it's efficient and widely used in traditional biometric systems. The deep learning approach usually uses convolution neural network to automatically learn fingerprint features
Excuse me,
from
ma'am.
image. Sorry, yeah.
I'm sorry to interrupt you. This is just a gentle reminder that 2 minutes are left for a presentation.
Sorry.
Sorry to interrupt you. This is just a gentle reminder that 2 minutes are left for you to finish your
Okay, sorry,
presentation.
sorry. Okay, it's okay. So I will go to the proposed system. So our proposed system consists of three fundamental stages: pre-processing, localization, and identification. In pre-process, we pass the database in different steps. Start with image transformation, image binarization, and pre-process. In localization, we detect orientation, and the system generate mark to separate the region from the background. And in identification stage, we apply deep learning for training and testing to achieve accurate fingerprint matching. So here, example for the obtained result, here for pre-processing stage, here for restoration stage. Okay, here for the correlation, sorry, here for the correlation, we use it so here in our system, rather than we use just samples from one, to use one sample for each individual, we use many images for same sample, and we estimated the correlation for these samples as a feature map for a classification stage. Here, they use database from Minis database and consists of two database, as you can see here. Here, some of the obtained result for restoration, alignment, and localization. Here, the output result, the best accuracy, 93 for the original data set, while after applying restoration and alignment, we get accuracy 98.33%. So, in conclusion, in forensic science, the smallest trace can reveal the greatest truth. So, our goal is to ensure that even degrade fingerprint under the most adverse condition can still speak with clarity and reliability through intelligent deep learning systems. Thank you for your attention. Hello?
You're audible.
Okay.
Dr. Fahmi, Dr. Al-Saidi,
Am I audible?
do you have any questions?
Yeah. Am I audible?
Yes, ma'am. You're audible.
Okay. So my first of all, a very nice presentation. Thank you, ma'am.
Thank
Only
you
the
so
one
much.
question: what you found as a challenging task while you are doing that pre-processing of fingerprints? Because the data is very sensitive, and if any of the age, if you are remove as a noise, so it becomes the challenge as per my knowledge. So what you found while you are doing the pre-processing of fingerprints?
Actually, the context of the image have a lot of noise, blurring, the ridge not clear, as well as the data is hard to use them directly. So we have to use different pre-process alignment to rotate the image. We have different data set, one of them with four, as I can show you in this presentation, I have one set of data. We have four finger for left hand and four finger for right hand and two thumb. And so how to cut these finger to make them 10 sample for each individual. The other database, it's all just thumb fingerprint. So these details make a lot of challenge in the in the beginning, but in somehow the procedure we applied a little bit facilitate this strategy. And I hope in my next research to get more improvement and to get more data set, maybe to improve even the obtained classification results.
Okay, how many images are there in your data set?
3. So for the pre-process, I applied peak to ratio, noise, mean square error, and signal to noise ratio. But for classification system, accuracy, F-score, precision, recall.
Do you face any challenges of overfitting or underfitting?
Um, you know, in the beginning, you face like this challenge, but you have to work on your tuning parameter to find the best setting parameter. So I tried to work on some trick, and I feel it's good
Okay, so
so
what
far.
ratio you kept for your testing and training images?
30% testing and 70% training.
Okay, so after many revisions, you came to know that it should be 70-30?
Yeah, 70
Okay,
to 30.
okay, fine. Thank you from my side.
Thank you so much.
Dr. Family, would you like to ask any questions? Thank you, Dr. Munira and Dr. Dabari.
Thank you so much. Thank you.
Our next author, Swamijit Maitli, is presenting Google Gemma-based abnormality detection in musculoskeletal radiographs. Mr. Swamijit, can you please share your presentation?
Am I audible and my screen is visible?
Yes, you're audible and your screen is visible.
Okay. Mm. So, good morning, everyone. Uh, Thank you for the opportunity. I'm Samjit Methi. I'm a PhD student here at University of Texas at Arlington. And today I'm excited to share our research on leveraging Google's MedGem model for automated abnormality detection in musculoskeletal radiographs. So today I'll show how we achieved a 92% of accuracy on this data set called Mura over the state-of-the-art model has been released before us with a 5% of improvement in our results. So what's the research context here? So automated abnormality detection is medical image is a critical component for computer-aided diagnosis system. For this research, we have used MURA dataset, which stands for musculoskeletal radiographs. And this one of the largest dataset available publicly with 40,000 plus X-ray images over 12,000 patients. And the traditional machine learning approaches to the medical image analysis requires an extensive feature engineering, manually designing algorithms to extract relevant features and all the edge detection. However, the emergence of foundation models like Google MedGemma, their large neural network pre-trained models on massive diverse datasets offer a new paradigm. These models have already learned rich generalizable representation of medical images during pre-training. So by fine-tuning them on our specific task, we can achieve a superior performance with less data and training time. So let's move on the next slide. And so what's the problem statement here? So medical image analysis presents several unique challenges that make it particularly difficult for conventional deep learning approaches. First, there is tremendous image diversity. Musculoskeletal radiographs are very widely used in anatomy, uh, and the image quality and the detection of abnormality there, like a hairline fracture in a wrist, it look different than a shoulder dislocation, but both have to be classified as abnormal by our model. So and the second is we face significant class imbalance in most of the medical images, including this Mura dataset also. And CNNs and autoencoders, these require extensive network engineering. Uh, we have to design every layers very specifically, otherwise the results will be not that good. And finally, we need models that are not just accurate on a single dataset, but robust and generalizable on all type of medical images. So our research objective has 4 pillars. First, we want to leverage the Google's MedGemma Foundation model, which Google recently released for with pre-training medical images. And secondly, we want to replace the traditional machine learning models like CNNs or other deep learning models for medical images. And we've enhanced our diagnostic accuracy while streamlining the training process. And we evaluate our model on 7 different anomaltic regions. So Mura dataset, this is provided by the Stanford University, and this has 40,000 of data with 7 anatomies like elbow, fingers, forearms, hand, shoulders, wrist, and it has a binary classification, like if the image is normal or it's abnormal. So for our data processing, the first thing we have done, in our data, there was all grayscale images, but the MedGemma vision encoder SIGLIP, that needs a 3-channel image. So we have to convert the RGB images to, grayscale images to RGB first, then to intensity, the normalization, medical images have a wide range of pixel intensity. So we generalize those to between 0 to 1, and we need a high quality image, and the vision encoder of MedGemma that also uh, takes input as 896 cross 896 images. So we have several dimension in our data set. So we rescale all to 896 to 896, and those all were high quality images. And fourth, we performed patient disjoint in study level. So we split the data set in 3 parts, like 70% for training, 15% for validation, and 15% for testing. Here in this diagram, you can see for the step 1, we converted those grayscale images to RGB. Then we normalized them, then we resized them, and we split them in training, testing, and validation. So here is the workflow of our experiment. So at the top, we have the input 896 by 896 three-channel X-ray image. Then we pre-process the image. Then we fed the image to the Google MedGemma CGLIP encoder. Encoder process the images. Then we put a three-head MLP classifier at the end, and that works pretty well. And I'll discuss more about that in the later presentation. So the encoder in the MedGemma model. So it's the CGLIP encoder, which stands for sigmoid loss for language image pre-training. It's a modified architecture of the CLIP architecture we have. It has first the patch embeddings of convolutional 2D layer with 14 by 14 kernel and stride. Then we have 4096 spatial positions with those numbers of patches. Yeah, then each patch is then projected into a 1152 dimensions embedding vectors, which are the output of our encoder and which we are using as the input of our three-head MLP classifier. And those patch embeddings passes through 27 transformer layers, which has the pre-training weights of uh, medical images from several studies. And we designed this MLP classifier head with three layers, like first the linear with the ReLU activation, and then we are rescaling that with using another layer. And at the end, we use a single neuron sigmoid for the binary classification. So why this architecture? Because we wanted something lightweight to prevent the overfitting with a powerful pre-training encoder, and we don't want a massive classification head. So we implemented this three-head MLP classifier. So for training, we have used a different approach. Like first, we try to not like we try to freeze all the layers in the pre-trained MedGemma's encoder. But we see that is not like optimal one. So with small learning rates, and we try to unfroze some layers in the MedGemma encoder, sometime two, then three, then four layers, and we compare those results. We'll show the approach later also in this presentation. And for experimental setup, uh, the machine in which we perform the
Excuse me.
experiment. Yes.
I'm sorry to interrupt you. This is just a gentle reminder that 2 minutes are left for your presentation.
Oh, thank you. So that consists of Intel Xeon processor and 192 gigs of RAM and NVIDIA RTX 5000 GPU. So here is the results, like per anatomy results. We almost get 95%, 94%, 93%, 92% accuracy for each anatomies. So if you see, the overall accuracy is 92% in our experiment. So here comes the unfreezing strategy. So first we compare the, in this diagram you can see, first we compare the head-only adaptation, then selective unfreezing. This takes less time to train and less time to get the embeddings, but this was not optimal. And the last one, you see, that we like unfreeze all the layers, and that was very higher computational cost. So in the middle one, you can see we tried to unfroze some of the layers and get the like latent vector from the encoder, and that approach really works well. And comparison with the state-of-the-art models previously. So the original Mura paper published by Raj Purkar and their colleagues at Stanford in 2017 achieves a 73% accuracy while they were using a DenseNet model. Then in 2021, he et al. They used a calibrated ensembled model, which get an accuracy of 87%. In 2024, Panhauer and their colleagues use a DenseNet 169 model to get the results on this data set, and they get 83% of accuracy. And our method got 92% of accuracy overall. So what are the key findings from our experiments? Like, we can use the MedGemma pretend encoder for uh, like small to create a small model for efficient classification, and selective unphrasing enhance the model's accuracy and model's performance. And if you are using a big encoder, then the small MLP layers or a small classification hint is okay to have it. And let's move on to next. So what's the clinical impact? So every clinics are not designed to have high cost GPU and high cost equipments. So if we want to run the big MedGemma model, that's not possible for every clinic worldwide. So this is an approach which shows like we can use the pre-trained modules from a model, and that can help the radiologist or the doctors as a companion, as a small companion, like this model with the small classification heads. And future work. So in future, if we want to implement with the large language model as the MedGemma is designed, so we can replace those large language models with small language models. So it can be lightweight, or we can try to divide the model in parts so we can load the model part by part. So it will be lightweight. And conclusion, like in a conclusion, our work demonstrate that medical foundation models offer a practical and effective substitute for traditional feature engineering in radiograph classification by leveraging Google MedGemma's model, especially the MedGemma. We used MedGemma 4B pre-trained model with Siglip vision encoder, and it achieves a 92% accuracy and 0.95 of AURC score overall. Thank you. Any questions?
Thank you so much, and a very good presentation from your side. Single question: why you selected the vision encoder here? What study you have applied for the selection of vision encoder?
Okay, so previously I have published several papers on medical images, like we have detected COVID-19 from chest X-ray images for those, and sometime brain Alzheimer for brain MRI image, and there is another paper on detecting cataract using the retina scans. So for those approaches, mostly I have used models like variational autoencoder to guess the features, or a residual autoencoder or a MedNet-based model. So there you can see we have to design the model very specifically for every step. And when I can see, like, there is a pre-trained model available from Google uh, with like several huge medical data. So I think that will be a privilege to get that model, get that encoder uh, to get the embedding vectors. Uh, and that features will be more like high quality features than the feature we get by feeding these images to a uh, new autoencoder or new model, which has no pre-training of medical images. So that's why I use this cyclic encoder from Medchem.
Okay, thank you.
Okay, thank you so much for the presentation. Very clear. I have one question regarding your project, in general. Are you
Yes.
involving a medical expert or consultant or final users in this project? Are you getting their feedback?
Not till now, but in future projects, we are trying to implement these things in sort of 2 or 3 local clinics, small clinics.
Okay, thank you. Thank you so much.
Mhm.
So we can go to the next presentation.
Okay, thank you.
Thank you.
Thank you. Now we have Deusdado Lionel presenting Menu AR, web-based augmented reality restaurants.
Hello, good afternoon, everyone. Are you listening?
Yes.
Okay, thank you. My name is Leonel Deusdado. I'm a professor in informatics field from University of Bragança in Portugal. And I will present the work Menu AR, web-based augmented reality for restaurants. Um, our work explores how web-based augmented reality can enhance the traditional restaurant menu experience. Instead of relying on static images or text descriptions, we propose a lightweight, full web-based IR system that allows customers to visualize realistic 3D dishes directly on their table using only a smartphone browser. So, traditional restaurant menus often fails to accurately communicate portions, size, plate style, visual representations. These limitations can generate incorrect expectations and even post-purchase dissatisfaction. Augmented reality offers a solution, a compelling solution for overlapping three-dimensional digital content on the real environment. In our case, customers scan QR codes and can visualize real size dishes positioned directly in front of them. Previous research shows that IR can increase purchase intention, improve customers' enjoyment, and strengthen decisions by confidence. By allowing customers to preview dishes in context, IR reduces ambiguity and supports more informed choice. So our goal was to design a full browser-based IR system that enhances customer experience, eliminating barriers such as app installation, platform restrictions, or property dependencies. Some related work have some solutions. However, many operates as a closed ecosystems or require dedicated mobile applications. So we must install their app before we can use the experience. As we can see here in this table, we compared our solution with other solutions that we find in the bibliography. Other web IR platforms provide browser-based experience but remain property and restrict development control over source codes and asset tables. The one that no requiring installing applications and have web access and open source, we have not so a lot of experience. Okay, in this stage, we can see the system design and architecture. We can see here some models of the photogrammetry because we pick real dishes where photographed from multiple angles using some applications that are already in the market for this with specific lighting conditions careful controller to reduce reflections and improve geometric fidelity and so on. The captured meshes require post-processing. We remove noise, filled holes, smooth textures, and simplified geometry. Optimization was essential because raw scans were too heavy for mobile web performance. Final models that we obtained ranged between 10 and 50 megabytes. While we know that this size is relatively large for web environments, we optimize it better and ensure acceptable loading times under modern 4G or 5G networks. In the system design and architecture, to expand our methodology to combine user-centered design principles with agile web and development, we generated a lot of tests to reducing the number of polygons in the model, compressing the textures and converting them to appropriate solutions, removing irrelevant surfaces such as table base captured during the scan. Our goal final is combine the user-centered design with a model that are liked and easy to use. In the implementation, the system was developed using standard web technologies such as HTML, CSS, JavaScript. We integrate for devices, for Android devices, and we must use Google components easily native in their phones. For iOS, more easy. They are already integrated, these capabilities, so we can have both solutions for both the most used devices. All content is served via HTTPS, so with security, and the system operates entirely without backend infrastructure, so no databases because the databases are installed in the phone, and the API, so no install in the phone, and the API is no required. This architecture ensures simplicity, scalability, compatibility across modern browsers such as Chrome, Safari, Firefox, and so on. So as you can see here, our app, we dedicate a lot of time design the simple interface focused in user experiences for more legibility, accessibility, and simple use of the menu. Each page presents a static photo for people that can't have these 3D IR options, but for the modern phones or devices is allowed to enable the IR button and see immediately the dish in front. So for the results and evaluation, the system was tested across multiple devices, as we speak before. In modern smartphones, IR visualization was stable and fluid. Loading times average approximately during less than 2 seconds and less than 10 megabytes for model. However, limitations were observed. iOS exclusively supports some kind of files, while Android requires IR core services for full functionality. Older devices were restricted, as we mentioned before, to a static 3D model in the browser, not in IR. Despite these constraints, no critical crashes or rendering failures were identified during our tests, and the results confirm that our solution can deliver reliable performance and optimization strategies if we apply careful all the circumstances that we talk about. So other results and evaluations, as we can see here in the table, our loading time is less or equal of the better in our comparative other companies, and the interactability is high, and we have and achieve a free and responsive UI. So, in the discussion, this work demonstrates that modern web technologies are capable of delivering sophisticated augmented reality experiences without requiring native applications. The immersive visualization enhances decision confidence and reduce uncertainty and problems when we are ordering and we don't know what we choose because we don't see what will come. Our solution excels in accessibility and openness, although commercial systems may still offer higher graphical polish or enterprise-level support. The study confirms the feasibility of web-based IR menus while highlighting technical challenges such as device fragmentation and performance viability. For future work, we can integrate a user feedback mechanism that enables a review for the dinners and generate more social proof and supporting. We can implementing real-time personalizations such as display dish calories counting of allergens as augmented
Excuse me.
reality overlays. I'm finished. Only 1 minute.
Okay.
Okay, thank you. And linking the IR menu to online ordering for payment systems could allow users to place orders directly after viewing dishes in IR, effectively transforming the systems into a comprehensive restaurant ordering platform. Okay, that's all. Sorry for the time and thank you for attention.
Thank you. Thank you so much for the presentation. Appreciate the work and the clarity of the presentation. Thank you.
Thank you.
No questions from my side. Let's continue with the next presentation.
Thank you, Leonel.
Okay, thank you.
Now we have Eduardo Mini Lopez presenting Vision-Based Operator Monitoring for Safety in Mining Teleoperation.
Okay, can you hear me?
Yes.
Yes.
Okay, good evening, everyone. It's a pleasure to be here at ICICT today. I will present our research titled Vision-Based Operator Monitoring for Safety in Mining Teleoperation. This work focuses on ensuring safety and maintaining situational awareness in remote mining environments through computer vision, bridging the gap between academic research and industrial application. This research was conducted at PUC-PR in Brazil in a strategic partnership with the company Teleop and the LACTEC Institute. I'm Eduardo Lamilopes, and I would like to acknowledge my co-authors, Alison Mafra, Luis Felipe Barroso, and professors Marcelo Pellens and Marco Antonio Teixeira. Our team belongs to the Cyber-Physical Systems Laboratory, and where we focus on digital transformation for heavy industry. So the context and motivation of this work stems from the rapid digital transformation that we have in the industry, where the mining industry is evolving rapidly, and the teleoperation, as shown in figure 1, has revolutionized the field by removing the operators from hazardous physical zones, by protecting them from landslides and toxic dust. However, this transition introduces new psychological risks. The operator loses the physical feel of the machine, and there is a total lack of haptic feedback and reduced situational awareness. So our goal is to ensure that the remote operator remains present, attentive, and in full control, even when they are kilometers away from the actual machine. So from the literature, the majority of the articles that we studied were using driving monitoring systems, or DMS for short. And the first question that we got was why we will not use standard automotive systems. And the answer lies in the figure 2, when the cabins that we have for teleoperation already have some security cameras, but they are side mounted to avoid obstructing the operator's view. And these cameras creates a significant perspective distortion and may generate some facial occlusion as well. Furthermore, the intense glare from the control monitors often blinds the traditional driver monitoring algorithms. So our approach was to build a specialized pipeline that works with the hardware already in the cabins, avoiding some expensive redesigns. So to solve these challenges, we developed a system optimized for the single monocular camera that we have inside the teleoperation cabin. Our system uses a unified monitoring framework, safety prioritized alert hierarchy, and our system also contains a lightweight execution. And instead of relying purely on facial features, our dual stream pipeline combined both a YOLO model for robust person detection, as well as an open source media pipe for skeletal tracking. We chose the YOLO model for its state-of-the-art balance between the speed and the accuracy in a low light environment. This also allows the system to understand the operator's posture, even when their face is partially obscured or washed out by a monitor glare. So our architecture is divided into 3 main phases. The first one is the pre-processing, where we define a specific region of interest around the operator, and we use temporal sampling to save some computational power, allowing it to run on standard cabin hardware. The second part, we run a parallel model on detection. So we detect both the operator presence and calculate the 3D head tilt and the wrist position of the operator. And the third part, we are using some filtering, where we use a temporal moving average filter, and this ensure that the alerts are stable and we prevent some flickering caused by some momentary movement or camera noise. So to manage the data efficiently, we established a priority-based hierarchy for alerts. The priority number 1 focuses on the posture deviation of the operator. So if the head tilt exceeds 20 degrees, the system will flag to the operator that it's a critical fatigue or a distraction event. Our second priority is to monitor the interaction zone that the operator have with the machine. So if the operator risks leave the controls, we trigger a hands-off controls alert. And our third priority simply covers the operator absence. So if the operator isn't working on the cabin, we can detect if we are having some commands sent from the cabin to the machine and intervene. So the key technical detail here is that we added a 60-frame rolling buffer instead of triggering an alarm or a single bad frame, which could be just a noise or a glare. The system requires a consistent detection over a window of time. So this ends up smoothing the data and prevents false positives from some quick or natural movements. So here in figure 4, you can see that the visual feedback of our system in action. So on the left, we see the hands-off controls monitoring alert in yellow, where the system tracking the risk of the operator and coordinates relative to that predefined blue box. So our region of interest is directly on the chair of the controls in the cabin. On the right, you can see how MediaPipe calculates the 3D head tilt, even with the side view distortion. And the system uses a clear traffic light color code. So in green, we have the normal operation. In yellow, we have the hands-off control warning. And in red, we have the critical posture deviation. So this visual layer is what allows the system to understand what the operator body posture is, even when the face is partially obscured. To validate all the setup, we used 120 minutes of real-world footage recorded inside active mining cabins. And this dataset was chosen specifically for the difficult, featuring extreme monitor glare and varying lighting. As researchers, we established the ground truth through meticulous frame-by-frame manual annotations. And this rigorous process was essential to ensure that our system's detection were being compared against 100% accurate human labels. Our results demonstrate performance across the board with an overall accuracy of 87%, but most notably, we achieved a 22% recall for normal operation and 83% recall for hands-off control detection. This proves that despite the non-ideal camera angles, the system can reliably distinguish between safe and unsafe behaviors. So you will notice that we have a lower precision of 0.42 here. And this one was one of the deliberate design choices that we had, and we call it the safety first bias, because in mining, a false alarm is a minor annoyance, but missing a fatigue event is a catastrophe. So we intentionally accept more alerts to ensure that nearly 100% of the hazards are captured. In the discussion and challenges, despite the success that we had in production, some challenges still remains. So we had streaming lighting shifts and monitor reflections that can still obstacle landmark tracking in very specific frames. And also because safety incidents are naturally rare, we had some data imbalances skewing our precision metrics. And finally, we found that the threshold calibration, like the 20-degree tilt, may need to be adjusted for operators of different heights to maintain perfect accuracy. In conclusion, we have validated the lightweight monocular system capable of achieving a high accuracy monitoring in complex cabins. And for future work, we aim to integrate some infrared sensors for the nighttime operations and to move forward to edge computing, reducing latency even further on the system. I would like to thank you for your time and listen to my presentation, and I look forward to your questions.
Okay. Thank you. Thank you so much for your presentation. In fact, my question is regarding if you would like to discuss the time latency. Um, uh, what is the time complexity or the time latency, or how it's feasible to go to edge computing, how it's time consuming the method, if we compare it also with the state of the art?
Great question, Professor. So the data latency in the cabins is treated as something very crucial because in remote mining operations, we are working on places that we don't have actually good internet connections. So we need to have a low latency. So in the system, we are trying to not use complex algorithms or anything that's very heavy that we end up taking a lot of time for the detection. So latency should be number one priority here.
Okay. Yeah. Thank you. Thank you so much. We don't have other questions. We can move forward to the next presentation.
Yes, thank you. Next, we have Neha R. Sainlin presenting zero-day attack detection using machine learning. Please share your presentation.
Yeah. Excuse me, can I get some time? I'm just trying to share my screen.
What's the issue?
Uh, it is asking for the permission to the Zoom. I just have to quit and reopen the Zoom.
Okay, sure.
Thank you.
I have a question. This is the last paper for today?
Yes, sir, this is the last presentation.
Okay. Yeah. The other point is a comment. I'm sorry for the beginning of the session. I was in another session, in fact, and then I was looking to the good or the right Zoom room to join you. So I was not here at the beginning of the session.
Oh, that's very understandable, sir. So thank you for joining us.
Thank you.
Yeah, are you able to present?
No, my schedule is tomorrow.
Can you see my screen?
I believe only a small portion of your screen is visible. You can share the file in the chat. I'll present it for you. But please be quick.
Yeah.
Sorry, apologies to the session chairs and participants for this delay. Please give us 2 minutes.
Hi, Sanskriti, did you get my files?
Yes, it's downloading. Just give me a minute. Does it need to be in the PPT format or would PDF also work?
Rudolph's work.
Okay. Is my screen visible?
Yes. Shall I start?
Yeah, please go on. Let me know when you need me to change the stats.
Yeah, sure. First of all, apologies for the delay and technical glitch. So, hello everyone. My name is Neha Saindane, and I'm presenting our work titled Zero Day Attack Detection Using Machine Learning. This research was conducted at the University of Maryland, Baltimore County, in collaboration with my co-authors Sahil Shahi, Shruti Dharmani, and Professor Faisal Kader. Although I'm presenting today, this work was truly a team effort. Yeah. So here's what I'll cover today. We'll look into the why zero-day attacks are dangerous, what was the problem motivation, what gap we identified in existing systems, that is research gap and contributions, hybrid detection architecture, then experimental results, comparative model performances, and SOC deployment benefits, and finally we'll see key takeaways. Now let's begin with the problem. So imagine a logistic company, millions of dollars in goods, continuous real-time network communication. Now think an attacker exploiting a vulnerability that no one has seen before. That's zero-day attack. Traditional intrusion detection system relies on known signatures. If attack is new, there is no signature. That is what a zero-day attack is. When we know the signatures, we match it with the database, that is traditional intrusion detection system. In logistic networks, where network breach doesn't just mean a loss, that is a blind spot we aim for. Now let's look at this visualization. This is like real-time network stream showing normal signal where traffic disrupted by sudden alert orange day attack waveform. We'll go into next slide, that is research gap and contribution. Most prior research focuses on single model approaches, but zero-day detection is complex. No single algorithm sees everything. So instead of trusting one super brain model, we built a squad. We design a hybrid framework, including k-means clustering, support vector machine, random forest, long short-term memory, and weighted AUs ensemble consensus mechanism. Let's look at the hybrid detection architecture. So here we use Kaggle dataset titled Zero Day Attack Detection in Logistic Networks. It contains 1400,000 network traffic records. They are a mix of benign activity and malicious zero-day attack activities. But computers don't see traffic as a hacker in dark room, they see spreadsheets. So we analyze 26 features, including net flow byte, that is volume of data moving, payload size, and content size, and so on. One fascinating observation was that certain malicious sessions reuse consistent user agent patterns, that is mimicking legitimate traffic. Then our architecture consists of 4 components, that is k-means, SVM, random forest, and LSTM. Each model sees the data differently. Instead of relying on one perspective, we combine their outputs using weighted AUC consensus. We begin with k-means clustering. Sanskriti, can go on the next slide. Yeah, so okay, so let's look at the model comparison. So we evaluated models using AOC, ROC. Here's what we found. SVM was 0.971, LSTM was 0.935, and random forest was 0.901. SVM performed best overall, but LSTM captured temporal patterns that static models missed. This proves why hybridization is important. Now let's look at the SVM. So we applied SVM, that is support vector machine, unlike k-means. It is supervised. It has the answer key. It learns from labeled past data. And mathematically, we call it a hyperplane. So it draws a line between widest possible margin, like between safe and malicious traffic. So in our study, SVM achieved AOC of 0.971. Then if we go to the next slide, that is LSTM. So sometimes single event looks innocent, but sequence tells a different story. That's why, unlike SVM, long short-term memory is a deep learning model with memory loops. If SVM looks at photograph, LSTM watches the movie. Like it remembers what happened 10 seconds ago or 10 minutes ago. It captures behavior like multi-stage attacks, gradual exploitation, uh, and patterns. So it achieved accuracy of 0.935, and it complements SVM by detecting time-dependent anomalies. If we look at the next slide, that is random forest. Yeah, so random forest is the consensus builder. Instead of one decision tree, it builds hundreds. A single tree can become biased in terms of feature selection. For example, over focusing on payload size. That's overfitting. So random forest averages across many trees, stabilizing predictions, and it achieved area under the curve of 0.901, which provides reliability and interpretability. Now let's go to the next slide. Let's talk about k-means clustering. That is, first k-means assigns a behavioral cluster. So that cluster ID becomes a new feature fed into SVM and random forest. Then for final alert decisions, we use weighted consensus. Like each model vote, but not equally. So let's talk about real world impact. So here we have applied SOC deployment where it reduces alert fatigue. We use cascading strategy. That means it collects all the outputs from different algorithms and make a decision out of it, which provides real-time scalability. And then to summarize this, zero-day detection requires behavioral intelligence. Hybrid modeling improves robustness. Our best AUC achieved was 0.971, where like temporal static clustering synthetically strengthens the decision. The framework is ready for real-time SOC deployment. So this was our four models competing. It is like four models. It is not like four models competing with each other. It is like four models are collaborating to give a perfect decision. So here you can see the references we use for our research paper. And thank you for your time. I welcome your questions.
Thank you. Thank you so much for your presentation. Can you tell me more about the data that you choose, where it was collected, when it was collected, and whether the data has been used in our study before?
So we have got the data from the Kaggle, that is zero-day attack detection in logistic network, and it consists of 26 features. Some of them are uh, purely zero-day attacks, and some are benign attacks. So, and the data set was updated last year, so we got it from Kaggle.
Okay, thank you. Thank you so much.
Yes, a very nice presentation No questions from my end.
Okay, and with that, we conclude all the presentations. I sincerely thank all our authors for their excellent presentations and valuable contributions to the session. I also extend my gratitude to all participants for being a part of this international conference. I hope this session was informative as well as insightful. On behalf of the ICICT team, thank you for your continued support during the 11th edition of ICICT as well as the previous editions. We look forward to welcoming you again to the 12th edition in 2027. All presenters will receive their digital certificates via email within 2 working days. The publication is expected to be available within 7 to 8 months. We kindly request your cooperation with the ICICT 2026 team during this process. I would also like to thank our session chairs, Professor Deepika and Professor Femi, for effectively chairing the session. We now present a token of our appreciation. On behalf of ICICT team, GR Foundation, and partners.
Thank you.
Thank you, ma'am. Thank you so much.
May I please request everyone to turn on their cameras so that we can have a quick snapshot of the session? Thank you everyone for joining us today. Have a great day.
Thank you.
Thank
everyone.
you. Have a great day.